Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Hello everybody and welcome to this presentation. In the previous lecture, we discussed the pre-treatment for the membranes that is very important to protect the membrane and increase the membrane life. In this lecture, we continue the section 3 with the second part as post-treatment, and in the end, we have an important exercise. Some important post-treatment processes in membranes such as disinfection, corrosion control, and removal dissolved gases and volatile compounds that I'm going to discuss each of which in the next slides. Disinfection. Disinfection is the process of killing or inactivating harmful and objectionable bacteria, cells, and other microorganisms by various agents such as chemicals, heat, ultraviolet light, ultrasonic waves, radiation, ozonation, and so on. What is the difference between disinfection and sterilization? Disinfection and sterilization are both decontamination processes. While disinfection is the process of eliminating or reducing harmful microorganisms from inanimate objects and surfaces, sterilization is the process of killing all microorganisms. That is the main difference between sterilizing and disinfecting. When does disinfection make sense? Microbiological quality of the permeate or filtrate is usually excellent after reverse osmosis, nanofiltration, ultrafiltration, and microfiltration. However, due to a damaged membrane such as broken fiber or contamination during operation, microbes can pass through. Generally, two methods of disinfection are used. Physical methods such as heating to boiling, incineration, irradiation with X-rays or UV rays, and chemical methods such as chlorination, ozonation, and so on. Corrosion control. In the United States, utilities spend over $19 billion per year combating corrosion problems in drinking water distribution systems. To avoid similar problems in waterworks or reclaimed water systems, methods for identification, control, and management of corrosion issues are needed, particularly in situations where water temperatures and pressures can fluctuate. Corrosion results from physicochemical reactions between a metal and its environment that lead to changes in the properties of the metal. In some cases, electrochemical reactions can act to initiate oxidation and dissolution of metals from piping and other materials that contact the reclaimed water. In general, corrosion can only occur in the presence of corrosion cell consisting of four elements: anode, cathode, electrolyte, and a conductor connecting the cathode with the anode as illustrated on this figure. Water quality considerations. A comparison of water quality variables that influence corrosion is given in this table. Water quality and hydraulic factors influence the potential for corrosion to occur in industrial vessels and conveyance structures. For example, pH changes have been correlated to increases in corrosion rates. Corrosion rapidly increases with decreasing pH less than 5. That increases acid concentration. High level of alkalinity over 150 mg per liter as calcium carbonate have been observed to cause increased corrosion of lead, copper, and zinc. Natural salts such as chloride and sulfate can act to increase corrosion rates, particularly at low oxygen concentration. This oxygen can induce and promote corrosion reactions, particularly under elevated temperature and pressures. In addition to chemical water quality, microorganisms in reclaimed water may directly or indirectly impact corrosion through the development of biofilms on wetted surfaces of pipelines, condensers, and process tanks. Microbial activity within biofilms produces acid-forming gases such as carbon dioxide and hydrogen sulfide that can lead to localized corrosion. Corrosion control is usually not required for ultrafiltration and microfiltration systems. For reverse osmosis and nanofiltration permeates with lack of calcium and alkalinity but the acidic pH. Some of the post-treatments to control corrosion, such as release of carbon dioxide in degasifiers, such as deacidification process, or addition of caustic sodium carbonate or bicarbonate to increase alkalinity and pH, but scaling potential has to be considered. Addition of corrosion inhibitor, addition of calcium chloride to increase calcium, addition of lime to increase calcium, alkalinity, and pH, but turbidity has to be considered. Combination of these processes. Removal of dissolved gases and volatile compounds. We have also discussed it in the pre-treatment. Dissolved gases have to be removed from water due to corrosion, taste, and odor problems. Hydrogen sulfide is a dissolved gas that gives water a characteristics rotten egg taste and odor. It corrodes piping, creates odors in the house, and turns water black. Hydrogen sulfide can cause odor problems at a concentration level as low as 0.05 mg per liter in well water. There are several techniques for removing hydrogen sulfide from water, including chlorination and filtration, manganese green sand iron filter, aeration, and some alternative systems. The removal of carbon dioxide is also the same as we have already discussed in the previous lecture. Carbon dioxide can be removed mechanically and chemically. Exercise. Selection of pre-treatment and post-treatment for membrane process. In the first exercise, for the purpose of drinking water production, three types of water sources with a given composition have shown that they have to be treated with the membrane. At first, which problems do you expect on the membranes as a consequence of the feedwater composition? Second, select the suitable pre-treatment and post-treatment for the prevention or minimization of these problems and change the process. And third, explain your reason for each selected process. Let's look at the water sources. The first water source is groundwater with a high amount of hardness, carbon dioxide, iron, sulfate, and conductivity, an intermediate amount of natural organic matter, turbidity, micropollutants, and low microbes. The second water source is surface water with a high amount of particles, microbes, high and low molecular organics, and low salts. The third water source is seawater with a high amount of hardness, salt, oxygen, microbes, and with an intermediate amount of particles and colloidal organics. To answer the first question, you should look at the composition that what problems will be taking place for the membrane in the presence of these substances. Total hardness and temporary hardness in reaction with carbon dioxide produce calcite, as you can see in this equilibrium, and calcite builds up a scale problem on the membrane surface. Iron, after oxidation, deposit on the membrane surface. Sulfate and conductivity cannot make a problem for microfiltration and ultrafiltration because according to this figure, ions pass through the membrane filtration, but they are removed using nanofiltration and reverse osmosis. Natural organic matter and turbidity cause organic and colloidal fouling, but due to the low concentration of microbes, there is no biofouling potential. The second question asks you to select a suitable pre-treatment and post-treatment for the prevention or minimization of these problems and explain your reasons. In the selection of pre-treatments, you must consider priorities. For this water source, at first I selected aeration to remove carbon dioxide and to oxidize iron. Oxidized iron can be removed using media filtration. Natural organic matter and turbidity can be removed using coagulation, flocculation, and sedimentation processes. In this regard, with addition coagulant before the aeration, flux can be formed and trapped by flocculant in the flocculation reactor and then can be settled in the sedimentation tank. As an option, potassium permanganate is used as a regeneration chemical to remove iron and hydrogen sulfide. As we have already discussed, the selection of a membrane to remove hardness depends on the concentration. If the concentration is high, you must use nanofiltration as a pre-treatment for reverse osmosis or some alternative such as ion exchange, but in low concentration, it can be removed using reverse osmosis directly. In this case, due to a high concentration of hardness, nanofiltration selected as a pre-treatment, and sulfate and conductivity can be removed using reverse osmosis. Before nanofiltration, anti-scaling applied for prevention of scaling. Biocides also can deter, render harmless, and kill living organisms. It is used to control and kill harmful and unwanted organisms such as bacteria, algae, insects, and rodents. Disinfection also applied as post-treatment in this chain. It has to notice that while the most common problems with groundwater is mineral ions such as calcium, magnesium, carbonate or bicarbonate, nitrate, iron, and so on, in surface water, natural organic matters, colloids, and microorganisms are the most common problems. In these surface water compositions, you have a high concentration of particles and microbes which cause particulate fouling and biofouling respectively. Natural organic matter also causes organic fouling. As pre-treatment, conventional processes such as coagulation, flocculation, and sedimentation are applied to remove particles. Microorganisms can be removed using microfiltration and ultrafiltration. Ozonation and biofiltration as post-treatment for microfiltration and ultrafiltration can be applied for the removal of molecular organics. In this seawater composition, there is a high concentration of hardness, salt, oxygen, and microbes, as well as an intermediate amount of particles and colloidal organics. Problems on the membrane surface include scaling, organic fouling, and biofouling. Removal of suspended particles and oxidized ions as multivalent ions can be accomplished in these modules. Granular activated carbon removes organics, but to increase its efficiency, sand filtration is required. Microorganisms can be removed using ultrafiltration. Salts such as sodium chloride as monovalent ions can be removed only using reverse osmosis. Exercise 2. In this table, seawater compositions have presented. First, determine the compounds that have scale potential respectively. For this, use the periodic table of scaling compounds that presented in this slide. Second, recommend the pretreatments, suitable membranes, and post-treatments based on the presented compositions for drinking water application. And third, determine the limitation of these ions in order to drinking water production according to the World Health Organization standards. This is your task. Please send your solutions for this problem to us. Now the section 3 finished. I will start the section 4 membrane design and evaluation with the next lecture. Thank you for your attention.